Okay, so question 11. We're told in a throw of a six-sided fair dice, a win consists of throwing a 1 or a 6. If the die is thrown 200 times, use a suitable approximation to find the probability the number of wins is 70 or between 60 and 70 inclusively. So we say let x be a random variable denoting the number of wins. Out of 200. Right? So then I can say that x is binomially distributed and there are 200 trials, and the probability of success throwing a 1 or a 6 is exactly 1 over 3. So I have to use a suitable approximation. So n equals to 200, p equals to 3. So I can say this is approximately, well, since n equals to 200, which is bigger than 50, is large, and np, which is equal to 200 times a third, which is approximately equal to 66.7, and nq, which is equal to 200 times 2/3, which is approximately equal to 133, are both bigger than 5. Therefore, x is approximately normally distributed with mean NP, so mean of 200 times a third, or 200 over 3, and variance of NPQ. So this will be 200 times a third times 2/3, and that's going to be 400 over 9. Right? So what does that mean? So now I have to use a suitable approximation to find the probability that the number of wins is 70. So the probability that x equals to 70 is approximately equal to the probability that 69.5 is less than or equal to x is less than or equal to 70.5 using the normal distribution with continuity correction. And so we key that into our GC. Distribution, normal CDF, and I need this to be lower bound of 69.5, upper bound of 70.5. Mean was 200 divided by 3. Standard deviation was 400 divided by 9. So we take the square root of 400 divided by 9. And we get the answer to be 0.5277, which is, to three significant figures, 0.528. So that's part 1. What about part 2? We're asked for the probability that x is between 60 and 70 inclusive. Well, that means that we're looking for the probability that 59.5 is less than or equal to x is less than or equal to 70.5. And again, we can just key this into our graphing calculator, can't we? So, very, very similar. Distribution. Normal CDF. This time, my lower bound is 59.5. My upper bound is again 70.5. My mean and variance are the same, so 200 divided by 3, and then I also want the square root of 400 divided by 9. What did I do wrong? Go to. What's that doing there? How on earth did I get that square root of? There we go. and that's 0.57622, 3 decimal places, 3 significant figures, 0.57623 SF. So that deals with the first part. And in the second part, they changed the game a little bit. So suppose the die is changed to a bias die such that the probability of throwing a 1 or a 6 is 0.92. If the die is thrown 55 times, find a suitable approximation to use a suitable approximation to find the probability the number of wins is at least 52. So again, that means our X is now binomially distributed, 55 trials, and probability of success of 0.92. So we should check that our approximation still works. So n equals to 55 is bigger than 50. That's a mess, sorry. Because n equals to 55, bigger than 50 is large. And what does NP equal to? NP is quite big. That'll be 55 times 0.92, which is 50.6, is bigger than 5. And what does NQ equal to? Well, that's 55 times 0.08, so 1 minus 0.92 is where 0.08 comes from. NQ is equal to 4.4. Ooh. So what does that mean? That means that whoever set this question has done a very, very bad job, because this one here means that I shouldn't be able to use my normal approximation. So this is too small. This is less than 5, and that makes us unhappy. So we can't carry on any further. But suppose we could. Suppose I change the numbers a little bit. Let me make this, instead of 0.92, let me just make this 0.90 exactly, right? Then NP is equal to, I don't know what it's equal to actually. I don't think I'm right here. So 0.9. So NP is now going to be 55 times 0.9, and that's going to be 49.5. So that's still big enough. And NQ is going to be 0.1 times 50, so that times 55. So that's going to be 5.5. Yep. So this is also bigger than 5. So therefore, X is approximately normally distributed with mean of 55 times 0.9, which is 49.5, and standard variance of 55 times 0.9 times 0.1. So that will be 4 point, sorry, I'm making a mess of that, aren't I? Oh, come on. 4.95. And so I'm asked to find the probability that the number of wins is at least 52, is bigger than or equal to 52. Well, this is approximately the probability that X is bigger than or equal to 51.5 in the normal distribution, so from 51.5 to infinity. And again, we can just use our normal distribution here, so second distribution, normal CDF, sorry, and our lower bound was 51.5, our upper bound was infinity, and again we had a mean of 49.5, no, not 29 mark, 49.5, and a standard deviation of the square root of 4.95. And so that gives us 0.184 to 3 significant figures. So just note that this question only works if I change the 0.92. If it's 0.92, there's no, I'm not able to do it. My approximation is not good enough because the distribution is too skewed. Okay, so we've got a bit of time left. Let's try example 12. Example 12, given that X is binomially distributed with mean of 80 trials and probability of success of 0.65, and Y is binomially distributed with 55 trials and probability of success of 0.35, state fully the approximate distribution of x minus y, and also find the appropriate value for this. So we know that this couldn't have happened in the past. It's been very, very difficult to compare because of the different number of trials and all that. So with approximation, we can now do this type of thing. So I'll leave the checking to you, but you can take my word for it that for both of these, n is sufficiently large and np and nq are both bigger than 5. So we should check n bigger than 50, which is definitely true, np bigger than 5, which I promise you is true, please go and check it, nq is also bigger than 5, which is true. So before we do find the approximate distribution of x minus y, I'm going to find the distribution for x approximately, and x is approximately 80 times 60.65 as its mean, and variance of 80 times 0.65 times 0.35 as its variance. So that means x is approximately normally distributed with mean of 52 and standard deviation and variance of 18.2. Similarly with y is normally distributed with 55 times 0.35 here, and then 55 times 0.35 times 0.65 here. So that means that y is normally distributed with 55 times 0.35 is, 55 times 0.35 is 19.25, and variance of 12.5125. So these are just approximations, but this gives us a bit of a sense as to what x and y may indeed look like. So we can, now that they're both normal, we can talk about what is the distribution of x minus y. And we, as we very well know, for this we can add the means together. Subtract the means from one another. So 52 minus 19.25. And we add the variances together. So 18.2 plus 12.5125. So what does that give us? That means x minus y has the distribution 32.75 as its mean and 30.7125 as its variance. And we're asked to find the probability that x minus y is bigger than 30. So we need to do a continuity to correction here. The probability that x minus y is bigger than 30 is equal to, with continuity correction, the probability that x minus y is bigger than or equal to 30.5. Can't equal to 30 here in the discrete case, right? So we just key this into our graphing calculator again. So distribution, normal CDF, and our lower bound is 30.5, our upper bound is infinity, and our mean was 32.75. Our variance, again, we need our standard deviation is the square root of the variance, and the variance was 30.7125. So what do we get? We get 0.6576828, or to 3SF that would just be 0.658. So that concludes the chapter on the normal distribution. If you have any questions, again, please comment, drop me a text message or drop me an email. I'll be more than happy to help out. Otherwise, I hope this is helpful to your revision, and we'll start on the tutorial next week.